Let's dive into 3D Gaussian splatting, a cutting-edge technique in computer graphics. It's a method that allows for the real-time rendering of highly detailed 3D scenes using only a sparse set of images, which is quite different from traditional approaches that rely on polygons or meshes. Instead, 3DGS uses Gaussian functions as the building blocks of a scene. This approach makes it much more efficient for representing and rendering complex shapes. Let's explore it in 4 parts. The 3D Gaussian splatting architecture. The main differences in how 3D Gaussian splatting and NeRFs handle 3D data. The adaptive density control improved the accuracy of 3D Gaussian splatting. The covariance matrix influenced the shape of a Gaussian splat. Now let's explore how 3D Gaussian splatting architecture achieves this. The first, core concepts of 3D Gaussian splatting. Let's break down the key elements of 3D Gaussian splatting. In this method, each point in a 3D scene is represented as a Gaussian splat. These splats have a few key characteristics. 1. Position, mean. This defines where the splat is located in the 3D space. 2. Covariance matrix. This tells us the shape and orientation of the splat. It allows us to represent different types of geometry, from sharp edges to smooth surfaces. 3. Color, RGB. The color information of each splat, which can change depending on the viewpoint of the observer. 4. Opacity. This controls how transparent the splat is, enabling effects like translucency or atmospheric scattering. Together, these splats form a continuous radiance field, which represents the color and density of light at every point in the scene, enabling photorealistic renderings. The second, the workflow of 3D Gaussian splatting. To implement 3D Gaussian splatting, the process follows several steps. 1. Data acquisition. The first step is capturing the scene from multiple viewpoints, typically using images or video frames. This data is processed using structure from motion to create an initial 3D point cloud. 2. Splat initialization. Each point in the point cloud is converted into a Gaussian splat. In areas requiring more detail, extra Gaussians may be added to improve accuracy. 3. Optimization. The Gaussians' parameters are refined through an iterative process. This involves differentiable rasterization, projecting the 3D Gaussians onto a 2D plane, loss function calculation, comparing the rendered image with the ground truth to guide the optimization, adaptive density control, adjusting the density of Gaussians to ensure better quality and minimize artifacts. 4. Rendering. Once everything is optimized, the scene can be rendered in real time, making it possible to interact with dynamic, high-quality 3D visuals. The third, advantages of 3D Gaussian splatting. The key benefits of 3DGS include 1. Efficiency. Gaussian splats allow for the representation of complex scenes with fewer data points compared to traditional methods. This leads to lower memory usage and faster rendering times. 2. Smooth transitions. The continuous nature of Gaussians enables smooth blending between splats, leading to smoother visual transitions and more realistic lighting effects. 3. Scalability. This technique can handle large-scale environments, making it perfect for fields like virtual reality, gaming, and digital twins. The fourth, the mathematical framework. At the heart of 3DGS is a solid mathematical model. Each splat is defined by its position, covariance matrix, color, and opacity. During optimization, we compute gradients based on the difference between the rendered images and the ground truth. This helps us fine-tune the parameters until we get the best visual output. In summary, the 3D Gaussian splatting architecture is a powerful and efficient method for representing and rendering 3D scenes. By using Gaussians rather than traditional mesh-based or voxel-based representations, it allows for smooth, continuous surfaces, better handling of lighting effects, and efficient rendering of complex geometries. Now let's compare 2 advanced techniques used for 3D reconstruction and rendering: 3D Gaussian splatting and neural radiance fields. While both aim to create realistic 3D models from images, they approach this task in very different ways. I'll break down the main differences between them. The first, Representation of 3D data. For 3D Gaussian splatting. 3D-GS uses an explicit representation of a scene by employing 3D Gaussian splats. Each splat represents a specific point in space with associated color and opacity values. This makes it easy to directly manipulate the geometry of the scene. The process starts with a point cloud created from images. Each point is converted into a Gaussian splat that can then be rasterized to produce 2D images. For neural radiance fields. NeRFs use an implicit representation, where a neural network models the scene. This network predicts the color and density of points in space, based on continuous input coordinates. NeRFs work by projecting rays from a camera into the scene, sampling along these rays to estimate color and density. Instead of using explicit geometric primitives like splats, NeRF treats the scene as a volumetric field. The second, data processing approach. For 3D Gaussian splatting. The approach here is more straightforward. It projects 3D points to 2D images and focuses on optimizing the Gaussians so that they match the captured images as closely as possible. Because it doesn't rely on complex neural network computations, 3D-GS generally offers faster training and rendering times. For neural radiance fields, NeRFs, on the other hand, project 2D images into 3D space. This process involves a much more complex training procedure, requiring the network to learn how to reconstruct the scene from multiple viewpoints. The training process can take longer and is generally more computationally intensive than 3D-GS. The third, rendering efficiency. For 3D Gaussian splatting. One of the key advantages of 3D-GS is that it enables real-time rendering. The splats are rasterized efficiently, allowing for quick visual feedback and interactivity. This makes it ideal for applications where real-time performance is essential. For neural radiance fields, NeRFs tend to have longer rendering times. This is because the neural network needs to evaluate each ray during rendering, which can be time-consuming. As a result, NeRFs are typically not suitable for real-time applications. The fourth, quality and detail handling. For 3D Gaussian splatting. While 3D-GS produces high-quality images, it may struggle with very intricate details, particularly when it comes to fine textures or complex lighting interactions. It works well for general scene representations, but may not capture the same level of detail as NeRFs. For neural radiance fields. NeRFs excel in capturing highly detailed visuals. They can produce images with intricate lighting and shading effects because of their ability to model the scene continuously, which allows them to handle complex visual details more effectively. In summary, both 3D Gaussian splatting and neural radiance fields have their own strengths and limitations. 3D-GS focuses on explicit representation, offering efficient real-time rendering, making it suitable for interactive applications, but it may struggle with fine details. NeRFs, on the other hand, leverage implicit representation through a neural network. They produce higher quality and more detailed images, but require more computation and time, making them less ideal for real-time use. Now, let's break down how adaptive density control makes 3D Gaussian splatting more accurate and efficient. Think of adaptive density control as the smart manager that dynamically decides how to use Gaussian primitives during rendering to achieve the best results. Here's how it works. The first, dynamic adjustment of Gaussian density. Adaptive density control utilizes a pixel error-driven approach to guide the densification of Gaussians. By assessing per-pixel errors derived from structural similarity or other informative metrics, the system can determine where additional Gaussian density is needed, ensuring that areas with higher visual complexity receive more representation. This targeted approach helps mitigate underfitting in regions that require finer detail, leading to more accurate scene reconstruction. The second, improved densification logic. The new formulation of adaptive density control allows for a more intuitive decision-making process regarding which Gaussians to densify. By breaking down per-pixel errors according to each Gaussian's contribution, the system can better track and respond to inaccuracies across different views. This results in a more effective allocation of resources, focusing on areas that will most improve visual fidelity. The third, pruning ineffective Gaussians. Adaptive density control not only facilitates the growth of necessary Gaussians, but also prunes those that do not contribute meaningfully to the scene representation. This dual mechanism prevents memory overload and ensures that only relevant data is processed, which enhances overall rendering efficiency without sacrificing accuracy. The fourth, correction of systematic biases. The original adaptive density control approach had biases in opacity management during Gaussian cloning operations, which could negatively affect the rendering quality. The revised method corrects these biases, ensuring that cloned Gaussians accurately reflect their contributions to pixel colors. This correction helps maintain consistency in visual output and improves overall scene representation. The fifth, enhanced gradient management. Adaptive density control adapts the gradients from different views based on the covered area, allowing for more effective growth of large Gaussians in critical regions. This adaptive weighting helps suppress floating artifacts near camera inputs and enhances the model's ability to reconstruct areas with insufficient initial data points. In summary, adaptive density control significantly improves the accuracy of 3D Gaussian splatting by enabling dynamic adjustment of Gaussian density based on per-pixel error assessments, enhancing densification logic, effectively pruning unnecessary Gaussians, correcting systematic biases in opacity handling, and optimizing gradient management. These improvements collectively lead to a more precise and efficient representation of complex 3D scenes, resulting in higher quality visual outputs. Now, let's talk about the covariance matrix in 3D Gaussian splatting and why it's so important. Think of it as the mathematical tool that defines the shape, orientation, and behavior of each Gaussian splat in 3D space. Here's how it works. The first, shape of the Gaussian splat. 1. Ellipsoidal representation. The covariance matrix is a symmetric matrix that encodes the geometric properties of the Gaussian splat, representing it as an ellipsoid in 3D space. The eigenvalues of this matrix determine the lengths of the principal axes of the ellipsoid. Larger eigenvalues correspond to more elongated shapes, while smaller eigenvalues create more compact forms. 2. Variability in dimensions. By adjusting the values within the covariance matrix, different shapes can be achieved, allowing for representation of both sharp edges and smooth surfaces. This flexibility is essential for accurately modeling various materials and geometries in a scene. The second, orientation of the Gaussian splat. 1. Eigenvectors and orientation. The eigenvectors of the covariance matrix dictate the orientation of the Gaussian ellipsoid. This means that by manipulating the covariance matrix, one can control how the Gaussian is rotated relative to the coordinate axes. Off-diagonal terms in the matrix contribute to this rotational aspect, allowing for non-axis aligned splats. 2. Tilt and rotation. In cases where certain off-diagonal elements are non-zero, the Gaussian splat can be tilted or rotated in space, which is crucial for accurately representing objects that are not aligned with standard coordinate axes. This capability enhances the overall realism of rendered scenes by allowing for more natural shapes. The third, projection effects. 1. 2D projection from 3D. When a 3D Gaussian is projected onto a 2D image plane, its shape transforms from an ellipsoid to an ellipse. The orientation and shape of this ellipse are influenced by how the original three-dimensional ellipsoid is aligned with respect to the camera view. If aligned directly with the viewing direction, it may appear circular. Otherwise, it may become elongated. 2. Impact on rendering quality. The ability to control both shape and orientation through the covariance matrix directly impacts rendering quality. By accurately modeling how Gaussians project onto 2D surfaces, 3DGS can achieve high visual fidelity in complex scenes. The fourth, mathematical considerations. For a covariance matrix to be valid, it must remain positive semi-definite. This condition ensures that all eigenvalues are non-negative, which is critical for maintaining meaningful geometric interpretations during optimization processes. Techniques such as gradient descent are employed to optimize these matrices while ensuring they remain valid throughout adjustments. In summary, the covariance matrix is fundamental to shaping and orienting Gaussian splats in 3D Gaussian splatting. It determines not only how these splats appear in three-dimensional space, but also how they project onto two-dimensional planes during rendering. By manipulating this matrix, one can achieve a wide variety of shapes and orientations, enhancing the accuracy and realism of rendered scenes.